So we'll move on with a Zoom talk by Rory Coles. Rory, are you here?
Yeah, he is.
Can you hear us?
Yep, hello.
You have 4 minutes. Please start.
Great, thank you. Hello everyone, my name is Rory Coles from the University of Victoria, presenting work in which we use semi-supervised learning for photometric redshift prediction. Having a large data set of reliable redshifts is necessary for studying the structure of the universe. However, the most consistent, reliable, and accurate method of getting these measurements using spectroscopy is expensive. And so we look to photometric estimation as a cheaper alternative. A lot of work in the past for estimating photometric redshift has been done using template fitting or by using handcrafted features, but deep learning, however, has a promise of being a cheaper alternative to using all available data that is coming from the large current and next generation surveys in an efficient manner. Specifically, semi-supervised learning allows us to use both data with and without associated labels, such as the spectroscopic redshift I mentioned earlier. This is important for our use case because, as I said, these measurements are very expensive, and so we may not have all that many. And so we have today a teacher-student paradigm that can use both data with and without labels. The teacher network learns in a fully supervised manner to predict redshift values from photometric images. The teacher then supplements the learning of the student network by generating labels for the student to learn from. To do this, we take unlabeled sources, perturb them using random augmentations, and then make a label using a prediction of the teacher network on the augmented images. The augmentations include rotating the image, translating it, adding noise, altering the color, and cropping away portions of the input data. These augmented images, as well as their generated labels, then make up a much larger data set for the student to learn from. Doing so allows for the student to learn on a more diverse and robust data set and actually outgrow the performance of the supervised teacher network. Both of our networks are the same size using the ResNet 50 architecture, followed by a density function projection head for probabilistic predictions. We have shown our method on data from the Hyper-Suprime-Cam program, and with as few as 2,500 spectroscopic redshifts, we get an average scaled redshift error of 0.03 up to redshifts of 4, with an outlier fraction of 3.6%. The results from using semi-supervised learning consistently outperform the same architecture when used in a supervised manner. These results take a simple network with limited data to well below the requirements of weak lensing for Euclid, and we hope to adapt them to more heterogeneous surveys in the future. I want to thank you all for your time, and if you have any further questions, please reach out to me on Slack.
Thanks, Rory.